Okay, in 3.4, we're going to look at real zeros of a polynomial. Learning targets, I can use rational zeros, the rational zeros theorem to find the possible rational zeros of a polynomial function. I can use synthetic division and factoring quadratic formula to find all real zeros of a polynomial. And I can use the remainder theorem to evaluate f of c. We'll take a look at that. So, some information that you should know. All right, let me just go through this slowly so we get through this and you can understand. Real zeros of a function f are solutions when f of x equals 0. On the graph of f, they are x-intercepts. So if there's zeros or x-intercepts, they are called solutions of f of x. So real zeros of f are solutions when f of x equals 0, or x-intercepts. We call them zeros, we can call them x-intercepts. Roots is another name for it. There are no easy formulas to find the real zeros of a polynomial of degree greater than 2. Obviously, if it was equal to 2, it would be quadratic, and you could use the quadratic formula. But we're saying if the degree is greater than 2, well, how can we find the zeros? Okay, let's go to number 1. To help find the real zeros of a polynomial function so that you can graph it, here are some things that you can do. Number 1, identify the maximum number of real zeros. It generally is the same as the degree of the function. So what is the degree of the function? Is it to the third power, fourth power? You could think of the second power, a quadratic. That'll be the maximum number of real zeros, which is 2. A quadratic can cross the x-axis at most 2 times. All right, but that's the maximum number. It can have less. It can have none, or even 1. Number 2. To find values for possible rational zeros, use the rational zeros theorem. All right. If there are rational zeros for f of x, they will be from the list made by plus or minus the factors of p over plus or minus the factors of the leading coefficient q. So when we talk about p over q, p is the factors, and we'll go over examples doing this. P are the factors of the constant term from your function. Usually it's the number that sits all by itself or sits alone. Divided by the factors of the leading coefficient. This is the number out front of your highest exponent. We call it q, plus or minus q. So the factors of the leading coefficient. So the factors of the number out front of the highest exponent. Again, we will do an example of this. Number 3, use synthetic division to find the possible rational zeros. Remember, if the remainder comes out to equal 0, as you learned in 3.2, if the remainder comes out to equal 0 using synthetic division, you know that it's a rational zero. If it doesn't and there's a remainder other than 0, then it's not a rational zero. Number 4, after finding one rational zero, determine whether or not the quotient is quadratic. All right, factor or use the quadratic formula if it's quadratic. How do you know if it's quadratic? The exponent now is 2. Remember, once you find or use a rational zero, you drop the exponent down 1. But if that quotient is quadratic, now you can solve by factoring or using the quadratic formula. But if the degree is still greater than 2, look for other methods to factor or test another rational zero from the list. All right, you're looking for other zeros. Last few. Number 5, graph using the real zeros, x-intercepts, the y-intercepts, multiplicity in behavior, and your knowledge of the power function in behavior that it imitates. So you're going to use all the things that you've already been using. All right, graphing the x-intercepts. What's the y-intercept? Set x equal to 0, and then find the y-intercept using your constant term. Multiplicity, is there a bounce back? If there's an even bounce back, if there's an even multiplicity, there's a bounce back. If it's odd, it passes right through that 0. What's the end behavior? Does it go up on the left, up on the right, down on the left, down on the right, or is it different up and down on left and right? What is your end behavior? And then your knowledge of the power function, like a quadratic, you know what a quadratic looks like, to the third power, things like that, along with end behavior that it imitates. You know that if it's to the second power, it should be a parabola. Last, number 6, evaluate the function for any other values of x, integers between the x-intercept that may help you graph. So if you have an x-intercept of 2 and you have an x-intercept of 5, maybe you want to find plug in x equals 3, x equals 4, and find out where the graph goes, and then find an ordered pair, and then you could graph that. Right? But only the integers between your x-intercepts. You could use synthetic division, and your remainder is your solution. That will go a lot faster. So this is just a little bit of information about where we're headed. Now we'll go, in the next video, we'll do some examples.